Good afternoon, everybody. Yeah, that's 3:30 here. Welcome to our body seminar series. Today it's my pleasure to introduce Dr. Ignacio Ciampitti. We were just joking that it's great to see so many people, and he was saying maybe because of you, I'm not saying it's because of you. Or let's say maybe because of Digital Ag. So there's a common theme here. So Dr. Ciampitti is a professor of Quantitative Agronomy and Digital Ag. He's the co-director of the Institute for Digital and Advanced Ag Systems here at Purdue, and one of the most recent Purdue. I first met Dr. Ciampitti about 8 or 10 years ago at K-State when we overlap a little bit. And at that time, he was already a very successful faculty with many students. I remember that, many students in your lab. So at K-State, his research efforts focus on optimizing nutrient management and closing new gaps in crops such as corn, sorghum, have soybeans, I guess, canola, a little bit, right? So here now at Purdue, he's advancing digital ag through data-driven approaches, integrating technologies such as satellite imagery, probabilistic analysis, and innovative visualization tools to help producers make more informed agronomic decisions. And that's the topic that he's going to be covering today. Perhaps one question that I have for you in advance, think about it, how through these institutes and your leadership, we are connecting multiple groups and different types of research across the university. And without further ado, let's welcome Dr. Ignacio Ciampitti.
Okay. Hopefully, if we turn on the lights, I mean, I'm afraid that many of you go on a sleeping mode. So I hope that I can keep you guys entertained for the next probably half hour or so. When I thought about the presentation, I was thinking about a couple of different examples. And this presentation is tailored for, I would say, a little bit of students too, because I want to make sure that we have many students in our disciplines in the College of Ag, that most of the times they don't see themselves working on digital ag, or they think about digital ag and they think something very dark or something too very high, impossible to achieve. And then we need to start thinking about how we start training the next generation of students that they are going to be tackling these big problems, okay? And I will be talking about data science a little bit because, I mean, we have a minor in data science, data-driven, and one of the comments that I get some of the times from our administration too, when they talk about data-driven, is that even in our department is that data-driven sounds like scary for many of the students. So we need to find ways of changing that and shifting that mentality. So I hope that some of the presentation will show where are we going in terms of digital ag. So, and as always, I mean, I put a definition on digital ag. I mean, it's just something that to keep us everyone on the same plane on saying what is digital ag. I mean, we talk about, many of you probably are doing something connected to digital ag. I'm sure that many of you are using sensors or are using any data processes or anything that is connected to, I mean, decision data collection, I mean, field sensor, remote sensing, everything that it can be included in a data pipeline that it goes from data collection all the way to a decision, and with the main goal of improving efficiency and sustainability is in some way defined as digital agriculture. So, and I want to make sure that you understand that the definition is very broad. I mean, the implementation and where you can see yourself, it can be in many different aspects on digital ag. And where are we at today? So if you look at the agricultural technological evolution, so we are here. As you know, the AI is becoming the main theme of many talks. And I think that many of you will just say, okay, I don't want to touch AI. I don't want to work today with AI. Unfortunately, many of the things that you're doing today, most likely you're already using AI. Or many of the things that you are even consuming today, they are in the process of the food processing. I mean, there is some AI methods and processing that is included there. So the time of the artificial intelligence is not something that's going to be in a couple of years. It's already happening, okay? And then we have direction even from the university to see how we start introducing AI in some of our curricula. Okay? And And I will show, I mean, we will show towards the end the importance of this artificial intelligence and data science. So technology, if you think about a farmer, if you think about things that you do every day, technology is everywhere, and we are collecting data all the time. One of the main issues that we face in the last 10 years is we went through yield monitors, I mean, soil sensors, I mean, weed sensing, drones, satellite data. The challenge is the conversion of that data into decisions, okay? You look at yield monitor, initially was starting in the 1990s. Most of the adoption of yield monitor and use of yield monitor information has been the last 5 years. And why? Well, because we have more companies, like for example, Climate was one, that they develop an automatic process of data, basically collection from the combine, processing, automatic cleaning, and now you have immediately using that yield monitor map to take decisions, okay? So there is something there. The bottleneck in the past was the data processing piece. And now today we are moving very fast on that aspect. And then one of the things that I emphasize in many of these, and when we work in the Institute and with people working with us in the Institute, is looking at how do we move quickly from data to decisions, okay? That's one of the big pieces that we are still getting there, and the other challenge that when you talk to companies and the industry is, they have at least some trouble on how to monetize the digitalization. Okay, so if you talk to some of the companies today, they say that they can develop tools, but then sometimes, I mean, to monetize and to have a sustainable plan that farmers will pay for that is a challenge. Okay, so unless they see the value, it's a challenge. So this came up yesterday, so we just put a paper that is Advances in Agronomy. Is just, we put a kind of a paper chapter that talks about a little bit about these different things on digital transformation. So, and give some examples of what is happening from a breeding, what is happening on agronomy. So I just put it there because I think that it took us some time to put all this together and put examples on how we can use data-driven approach to select varieties, for nitrogen management, and for some of the examples there. So what is quantitative agriculture? Many people will say, what is that? And I think that we have been seeing all the time. I mean, most of the times we see people that are working on one topic, but I have already seen many faculty here that they are working without probably them recognizing or knowing it. They're working on multiple topics. They're working on collecting field data, sensing data. And the challenges in the past was the lack of connection. Sometimes we were having people that they were working in agronomy only, or they were working on collecting data in the field, but there was no connection. And then the challenge that we are bridging now is how we can move in the connection. So that's one of the things that why we start talking about this idea of the Institute for Digital Agriculture and bringing people together, because for doing this, moving on this direction, it doesn't take one person. It takes building teams, and it takes building this idea of how we can put people together with different skills that they can start talking to each other. I mean, and I give one example because this is one example that we did a couple of years ago, but it's moving from, okay, in agronomy, we usually do many studies. We are really good at doing it, putting plots in the field. We are awesome in plant density, in nitrogen, but most of the times we use that information that comes from one location to provide a recommendation. Okay, and one of the challenges is that sometimes we use extracted information coming from the field and provide a recommendation. So, and then what we start challenging many people is to start thinking about how do we move from this traditional approach that is getting the data from one specific field, soil type, and weather scenario to build probabilistic models, which basically you infuse the data and you start building models that they have some level of probability. So, and I took one example. We took all the data that we have from the US on density, yield response, corn yield response to plant density. And there are two options here. You can just grab all the data and publish as a synthesis paper and say, okay, here is all the insight, here is optimal density in this location, here is optimal density in this location. Or you can grab all the information and start building a probability model that incorporates basically uncertainty. Okay, and we're going to talk a little bit about uncertainty. Okay, and uncertainty means that now we are not defining a number, but we are also defining the number and what is the error around the number. Okay, And I will say that at least from the agronomy perspective, I mean, many times we just, and this is being pushed by farmers too, or by our stakeholders, they usually want to have a recommendation and they want to know a number. Sometimes if you say, oh, there is an uncertainty, they look at you and then just tell me how much do I need to apply, okay? But on science, we have an uncertainty. And then in this example, what we did is just putting different data layers. I mean, from the field, from data from soil, remote sensing, weather, and we use Bayesian approach. So some of the Bayesian statistical model help us to define uncertainty and build probabilities. And then what we start looking is, okay, what was the growing season for the last 30 years? And we look at different months in the growing season, and we look at the variability between precipitation and temperature. And here I'm only plotting two different scenarios. One of the driest year, 2012, and the wettest years, 2018. And mainly what I would like to show is, like, if you go to the dry year, if I can put this down. If you go to a very dry year, you will start seeing that the probabilities of plant density. So, and I can translate this into plants per acre. So for example, 10 will be, or 11 will be closer to 40,000 plants per acre. So you start seeing that in many situations, you have higher probabilities of higher densities here. And as you are getting into this area of the US, was less precipitation with less probability of basically the optimal plant density was smaller. And if you go to a wet year, so the wet year in a rainy season, you start seeing that most of the times there has been more changes on these areas, that they were more, mainly in Missouri too, and in Kansas in this area, Nebraska. Some of the areas that they were more prone to that dry weather in 2012, 2018 was a kind of a rainy season. So the optimal plant density for that was increasing. But here is just an example of showing how you can build probabilistic approaches, I mean, on the modeling, rather than just use point observations, on using point observations in terms of yield response to plant density. So let me show you a little bit about satellite, because many people talk about this, but we don't really focus too much. We have a project now that is with NASA, that one of the main goals on that project is called FIAT. So it's basically Farmer Innovation Ambassador Team. So we're bringing farmers from multiple states. And the main goal is to have farmers helping guide how NASA should basically develop products for them. Very challenging, because at the end of the day, many of the farmers, when you talk about NASA, they think about rockets like everyone else, but they don't even know that NASA has a section that is agriculture. So NASA has a section in their budget that is very, very, very small, but it's called agriculture, okay? And the people from NASA Ag go together and they have a consortium that is called NASA Acres. So the NASA Acres consortium is domestic. It focuses on applications that satellite can do for farmers, for stakeholders domestically. And then there is another consortium that is called NASA Harvest that focuses on the international piece of the NASA Ag. So, and as you see, satellite has evolved very quickly, but mainly in the last 10 years. We went from, since 1970s all the way from now. And if you look at now, with the new US mission with India, so we're going to have very high resolution and many spectral bands that they are going to be available just in the next months, okay? Many of these bands will help us probably to target some applications, like, for example, if we're looking at water stress, or if you're looking at nitrogen stress. And there is another mission that is focusing on hyperspectrum. But the question is, what do I do with all these satellite data? So, and there are multiple examples here. I will show just one specific field. So here is one field. You need to believe me on this. And I will show you what happens if you use different satellite sources. So this is MODIS, 250 meter, PROA-B, 100 meters, Landsat, Sentinel. So what happens when you compare all the sources? So as you are getting to basically Sentinel, for example, as you start getting even to the new ones, they are 5 by 5 meters or 3 by 3 meters. Now you start seeing things on the field. So now you look, for example, this Western Kansas. So you look at these irrigation pivots and you start seeing some problems. If you look at this source, also open, and most of the times you have more availability on this one, but most of the times, I mean, if you want to look at within field variability, it's really hard to look at with just MODIs. All these options on satellites are open. And there are many things. If you look at how things are evolving on the satellite pieces, like the last 10 years has been impressive, no? I mean, even now from disease monitoring or from pest surveillance. So we are looking at many things. I mean, the initial ones, if you look at how many studies, research has been done on crop classification, for crop mapping, phenology prediction. I will show one example, yield forecast, many. But it's impressive how every week, every month, you start seeing more uses on satellite. The only thing why I want to focus on the students too is like, when you talk about these things, we need to have people that they know this. We really need to start training people that they are good on, do you know how to use R? Are you good at coding? Do you usually use Python? Okay. Do you understand what a crop model is? Can you integrate crop model with satellite? Okay. And that's a challenge. So it's really focusing on how you can get some skills. That is what many people will call here data science skills. But these are skills that you need to have in order to be a little bit more multidisciplinary, like trying to be a little bit out of that area of expertise, no? And sometimes it's really hard to find that people. In fact, I would love to see more ag people that we can convert them, I can evangelize them, and I can convert them into ag data scientists. Sometimes we finish basically bringing people from computer science, and then we convert them in ag, which sometimes is challenging, very challenging to do that process, because it's better to work with people in ag and then see if they can train on these skills. I will give one example. I mean, for people that they say, okay, can we use satellite for crop phenology? We have studies. There is new data now, for example, that is, for many of you that they are familiar with Planet. I mean, Planet has data that is Planet Fusion, that basically is data that is a day by day. So you could have data that is basically with a resolution, a temporal resolution that is day by day. The question is, how do they do this? Because you will say it's impossible. Yes, it's impossible. The way that they do it is by using all the satellites that are available, and they basically build synthetic data. Okay, is it good? It's really good. The challenge is the amount of gigabytes, terabytes that you need is impressive. So we are talking about we're talking about a lot of data. So in this case, we focus on an example in Western Kansas. We look at using Sentinel that has less resolution versus Planet. And we have data from the field because we have working with a consulting company that they collected data. And this consulting company one day was walking around the building, and they say, we don't know what to do with this data. And I'm like, do you have data from these many fields? And you have people that they went every week? Yeah, but we don't really know what to do with this. And I'm like, okay. So I convinced them that they would be a good idea to share with us. And then we developed for them some kind of a small prediction of phenology. So, and what it does is very simple. It's just following the trajectory of BIs. Like in this case, we use enhanced vegetation index. It's called EVI. And it's just, you can test many different spectral indices. But most of the times when you look at any crop, you will see that you have a peak around flowering in corn, for example. As the corn is senescing, it's going down. So you could start comparing, for example, fields that are under stress versus fields that they are not under stress. Or I can tell to Christian, oh, I know what fields you have tar spot. Because I can start looking and studying all the drop. And I can tell, oh, this field that had tar spot did this. And this one that basically didn't have tar spot was basically having a normal senescence. Okay, so you can start mapping disease progression and disease incidence very quickly. So this is just an example of classification, precision, recall. But basically summarize, I don't want to get too much in this. The Planet Fusion data is a day by day is super precise. When they ask me, I say, we don't need that. For an agronomist, if I have data every week, that's enough. Having daily data, honestly, the plants usually, when we are talking about changes in the crop phenology, doesn't change by day. Usually we change like sometimes every 3-4 days, okay? in a really rapid moment. So here it was a classification that we built for them. So we have basically identification of all the different stages. And now we have this probability map that basically they're using in this tool. I know because they usually touch base all the time with us. And we're building this tool now for other crops in other areas in the Great Plains too. Many things, yield forecast every day. If you go to, for the students too, if you go to the literature, you will find every day, I will bet this, a paper on yield forecast. I mean, there's a paper that they say, now we improve yield forecast and our error is, so every day there is a new paper with a new satellite, with a new type of data science approach to estimate yields. And the question that everyone is asking, why we don't have a satellite-based yield forecast rather than rely on USDA, I will say that it's more because of other things. And sometimes having too precise estimation might be not too good. It's good to keep some uncertainty on that. But you could get today very close and we can start predicting for corn yields. I mean, we can make predictions with probably a 10% error, which is 10–15% error when you look at the predictions is really good. You can make predictions, I mean, usually by mid to late July. So, and remember that usually the USDA report with the yield forecast predictions is coming usually in August 10 to 12, right? So the first, second week of August is when they release the prediction of forecast for corn in the US. I mean, we prove that we have a publication that shows that we could do it easily because it doesn't change too much 2 or 3 weeks earlier with satellite. And satellite is a proxy of yield monitor. We have one farmer one day that, and this is in Brazil, in fact, that they have 8 years of yield monitor. And then I say, what happens if a farmer doesn't have yield monitor data? So imagine that you go and talk to a farmer and he doesn't have any data from that field. And you will say, I don't even know what happened in my field in the last 8 years. And you want to go and buy that field. So here's an example of comparing using 8 years of building zones, management zones using yield monitor data versus using basically a combination of different satellite with different basically vegetation index. So you could basically map many fields today with satellite. You can just build those maps and you can build basically the variability. So here, basically these variabilities, different areas with different yields. So in many situations, many people is using this even for conservation purposes. So all the CRP. So when you're looking at mapping CRP, when you don't have any data on CRP, so you can use a satellite just to go back and then kind of a play detective, no? We also did this with another student that was on my team last year. We have data from farmer fields in Argentina that they were in wheat. And we built a model, it's very simple also, it's a model that is based on basically understanding what is the fraction of intercepted radiation. So we look at intercepted radiation during the season and we use the satellite to give us an estimate of the intercepted radiation. So we built this model and then we were able to basically now improve predictions on yield forecasts on wheat tremendously. The only thing that the forecast, or one of the things that is interesting, how satellite has limitations. It happened that we start seeing in some of the predictions some problems, and we found that some of those fields were the fields that they have like a late frost. Why? Because most of the times if you have a kind of a cold weather coming at the end of the season, it was impacting the yields, but the canopy was staying green. So you have some senescence, but I mean, was not being captured by the satellite. So and we start seeing when we go back and talk to these farmers that there was, I mean, and we look at the weather data. So there were some of these fields that they experienced some cold weather and the yield was impacted by the canopy was not. So, and that's one of the things that you need to remember, know that satellite has some limitations. I mean, unless you start putting together satellite with weather, so they have some limitations on. Using satellite, this is something that we are working with, in collaboration with the University of Illinois, and then they were flying some fields this year. And also there is another company that is, that I'm advising, guiding them on using satellite for nitrogen. So this is basically connecting a plane using hyperspectral camera, looking at multiple fields during the growing season, and then using some satellite data to start looking at nitrogen deficiencies. And this is an example of the project that we have with NASA Acres. And what we are doing is looking at different reflectance. So when you're looking at hyperspectral, you have multiple ones. But what we know for sure is, I mean, in many situations, what we are doing is this: we're building the dilution curve. So as the plants are growing, nitrogen is diluted. So this is called nitrogen dilution. So what we start capturing is basically that these are plants that were really small in the season, and then as the plants are growing, we start predicting what was the changes on nitrogen concentration. So, and the main goal was to then improve the predictions of that we are doing now is like we're improving the predictions of nitrogen nutrition during time. So now we will be able to, I think that probably we are processing the data from this year. So now we will be able to start looking at farmer fields and conditions and know exactly what farmers or fields they have excess or deficient on nitrogen. Okay, because we're doing estimations individually of nitrogen concentration and biomass, and then from there we are estimating what is the total uptake. Here is one that I think that is from Champaign County. So basically look at different canopy nitrogen content. That was in 2024. So quality. So you start seeing that many people slowly start talking about quality. But quality is a challenge. If we talk about protein and oil, so I think that there is more people talking about oil today because of the biofuel and talking about basically can we build predictions. No? And we started this project 3 years ago. So when we started the project, I mean, we're working with the people from soybeans, they were super interested in protein. They say protein is the next thing, protein for animal nutrition, everyone will pay about this. After 2 years, basically all the protein companies disappear and the animal consumption, I mean, if you look at poultry, chicken, and so far, I mean, they're not paying premiums for protein. But interesting enough, there was a switch because we were collecting data from farmer fields. We were basically going to these farmer fields. We have a protocol. We were collecting samples from multiple sections of the field. And we were basically doing both protein and oil. And suddenly last year we have like airlines company coming and saying, do you have any information about how much oil is on the country? And you say, well, probably we can get a good estimate. And how do you do it is, I mean, again, most of the satellite is usually indirectly. So what we are doing is we're mapping basically canopy or green chlorophyll. And then what you're doing is a proxy of that is protein. Protein predictions are really hard to get because usually protein and yield are opposite. As soybean yields are going up, protein is going down because there is dilution. But interesting enough, oil is very interesting because usually with high yields, you usually get more oil, okay? Because the oil concentration usually is very stable, but as you are getting more yield, you are getting more oil productivity, okay? And we start building this idea. So we start testing different, this was one student that we published a paper, also part of the NASA Acres project. And we are now expanding. In fact, we are working this now in sorghum, first in wheat, and now we're gonna work on some sorghum trials. And here is some of the examples of the predictions that we have at the field. This is using satellite, okay? Well, our main idea was at the beginning, we say, oh, we can use this as a pre-mapping. The farmer will know before it gets into the combine, what is the variability of protein and oil in the field, okay? So then when you get into the combine, you have the chance, if you want, to start doing segregation, okay? But then we start talking to other companies and they were interested on something else. They were not only interested on the farmer itself, but they were interested also on trying to understand how much variability is on different sections in the field. So we just finished publishing another paper with all the database because we basically collected the last 3 years close to 350 farmer fields across the entire US, 13 states, okay? And then when you start integrating this data that is at the farm level with some satellite data, then we can start getting predictions. I mean, and then we start building predictions of protein and different sections in different parts of the states and oil. And then for sure, the most precise, if you want to say, is oil predictions are really good. And if you look at where oil usually is concentrated, most of the high oil contents are usually in Iowa, Illinois, and Indiana, because it's where we have usually the highest yields for soybeans. So those are the situations where we can start seeing that in terms of oil prediction and high oil in these areas around here, and then some around the Mississippi. So, but in the rest of the places where you have lower yields outside of the kind of a corn belt, then that oil concentration is kind of reduced. So very quickly, I will just show a few things that we have been working in our lab here. So this is something that we're working with some breeders this year. We have a student working on identifying panicle traits. Like this is like many people working in sorghum. That is a sorghum plant. So many people doesn't want to count grains. And here is an example of how you can start using, like, for example, RGB or proximal sensing. And then we are connecting this with some computer vision models. And what we are doing there is just to show an example of how do you segment the panicle, do the separation, and then do the estimation. So this is one example that we are working towards developing. And we have a prototype application that basically taking one picture, you can now start getting estimates of the total final number of grains. Okay. And if you look at the grains number, it's around 3,000. So no one would like to count 3,000. Many people would like to probably count in corn, but on this, forget it. Most of the times they look at this and saying, yeah, sure. So now at least they should take a picture and they will be able to get some kind of a good estimate. Okay? And that's one of the things. The other thing that we're doing is also looking at phenotyping. So if you think about phenotyping in the field, it's very challenging. Everyone is doing phenotyping in control conditions, phenotyping facility or a greenhouse, but no one wants to touch or no one wants to do anything in the field. And why? Because it takes time and it's a problem. So, and we have done this study. This was a year ago that we were looking at plants with different architecture. And we start building predictions. This was for a master student that we start building predictions of canopy architecture. And we have basically all the determinations of different leaf angles, leaf length. So moving forward to find a way to obtain phenotyping trait measurements faster. And based on some of them, they derive only on just having RGB with some spectral camera. Like many times using, for example, what we'll show now using LiDAR. And here is one of the projects that I was discussing with Christian many times. It's like we talk about many companies are doing this, they're counting grains. So you could find even open source software that will do this. So if you take a picture, it will count how many grains you have for corn. But for us, that was like a space that we don't want to compete because there are many already kind of companies that open source that they basically are doing that. You take a picture and they can count kernels. So what we decided to do was moving into a different direction. So let me show you just 1 second. So as I mentioned before, so this is a little bit of the pipeline. So we decided to move on rather than just to wait until the end of the growing season to obtain the final yield. We say, why we don't just build a model that will give us a potential yield? And why we say this is because many times when farmers or anyone that they go to the field, they're taking decisions on applying fungicides or applying herbicides. They're taking those decisions mainly because they are seeing a disease and they're seeing that it's moving and they say, okay, I need to apply. If not, I will lose yield. But one of our questions is, what yield are you losing? How much are you losing? Do you know what is your yield potential? And then what we start building is this approach that basically is like a mix of RGB. I mean, because basically what it does is just using RGB for doing segmentation. And then one of the main things is like trying to get an estimate of what is the size of the ears. Because based on that size, we know how many kernels we can host. And that's pretty standard. So we basically collected, this year we finished collecting, I think it's 2,000 ears in total. And then we did pictures every week, or almost every week. So we have around more than 10,000 pictures of those ears from 20 different genotypes. Why? Because we are building a model that basically is connecting the optimal maximum number of kernels with the size of the ears. And we are testing that model across different genotypes. And because it's allometric models based on volume size, So we can just basically start giving you by pictures, what is the potential yield for that plant, okay? So, and this has potential applications in multiple things. You can use this for, you are scouting. You can just go out to the field and take pictures, or you have a spraying. So you are spraying, so you need to know what is your return of investment. So you could start having this type of, sensing in multiple things. And the process is very simple. Now we're working on building or improving this year the method, the automatic process and the cloud point. And the idea is at the end of the day, what you get is basically, we're now working on building the entire implementation. So we are collaborating with NanoHub. And then what we are doing with them is, okay, we are building the entire pipeline from sending the pictures from the field. And there is a machine learning model running that we developed that give us basically what is the prediction of the years based on the picture. And we also have measurements. Now we have ground truthing because we have 200 years that we're going through now. And then what we're doing with that is getting an estimate of what is the yield based on volume. Okay, so it's pretty simple. It's nothing too complex, but it's basically what you see is that it's connecting a little bit the physiology, the allometric models, that the physiology of the plant, the basic things that happen all the time with just technology, and building these applications. And this is what we are doing. So for example, now this year we're looking at deep learning models. So we're also collaborating with Bedrick. I don't know if the model, let me see if, no. So I did have a nice video, but of course it was not coming through, but that basically now we are reconstructing the years. So basically we are building this is a 3D model of the years. So now, for example, what we are doing is we are building an application. It's a web app that you take a picture in the field and tells you exactly where you took the picture and gives you exactly basically the 3D reconstruction of the year with all the basically volume, size, yield prediction. Okay. And again, it's connecting multiple disciplines because we are a little bit of an expert on one discipline and then we're connecting with other disciplines to help us on the data architecture. Last piece, mainly focus on the students. I usually say to my students, at least in many situations, is the paper is not the last step. And usually when we finish publishing a paper, we like to see if we can start moving on developing applications. And the challenges on doing that is that I would say today is less challenging than 5 years ago. 5 years ago, when you wanted to build an application was too complex. Now you have shiny app editors. You have so many things that you can just explore. And you're going to start putting your data into really dynamic tools. And I will show some of the things that we did by grabbing papers that we publish a paper and we finish publishing the paper and then you can build an app immediately. So you can show to someone, my data is here, it lives, it's available, and now you can visualize it. Okay. And it helps with reproducibility. So the other thing that we talked to Christian quite a bit is about this idea of where is the data. And I know that Jeff also has the same passion. Open databases. How do we develop ISO standard? How do we make sure that the data doesn't end when the student is leaving? How many times we have students leaving and you start reaching out to the student after a year and saying, where is the data? And I think that this idea of how we start building data pipelines and make sure that data is open and reproducibility is important for the future. I always say to someone, and I make a joke, someone 50, 60 years in the future will look back and say, who were those guys? Because I'm doing that when I'm looking back. I'm looking back and saying, why they didn't share? I'm looking at the publications and I say, why they put a p-value on an average? Why they didn't share the treatment means? Because sometimes I want to go through these publications and grab the data. Mm-hmm. And I'm building open databases. And I look at the paper and they say, we did 11 sites, 10 treatments, 20, and I'm looking, oh, this will be like 2,000 data points. And they say, there was no result, no significant, this is the average. I'm like, ah. So, giving an example of the lack of standards. In many situations, we have lack of standards. And if you look at other disciplines, they are really well ahead. If you look at plant breeding, and if you look at even the medicine piece, they are really well ahead of how they are handling data, how they are opening, sharing the data. We still are at least 10 years behind, I will say, to keep it optimistic. And we still are missing, I mean, the component of accessibility and open databases. So, and total disclosure, I love open databases. And my students, they know that. And then every time that I come in with an idea, and I talk to another guy from Christian on his lab, and then I hope that Christian is not hating me now, because I know that it takes a lot of time to build open databases. Okay, and we are talking about how we are better in trends of using AI, and we have some guys on the team that are helping us to see if we can start cutting time, because every database that we built in the past, it took us sometimes 4 people, 4 months. Simple as that, no? Like going through publications, curating publications, developing columns, I mean, standardization, and then going through a journal. For example, I'm editorial board member for Nature Scientific Data, and they publish open databases. So if you want to get there, you need to have high standards. And it's important to do that because we are leaving something behind of what we do. So we're leaving something that other people can use in the future, okay? And that's something that, when I'm looking at my team members, it's very painful. It's very painful, it takes time, but it's very, very useful. As an exercise for students that are starting their career, having the experience of reading papers, learning from the papers, extracting data, looking at the data and putting that data all together is a process that is very, very fruitful, okay? I mean, I know that it's for few, but I would recommend for any PhD student that they can to do that as almost a first project, building an open database, because then you will learn what are the gaps on your topic. What are the things that no one really answered today? Because when you look at that database, you will have more questions, new questions that are coming that you say, no one look at this. So the level of I mean, I will say creativity will go up. And just to close very briefly, we have a few data. Shiny, this was something that we developed with Iowa soybeans. It was very simple. So we have like a yield monitor data. So I mean, this is more dedicated to agronomists. So for example, you know that, I mean, every time that you get inside of a plane and you are flying anywhere, before any of these pilots are inside of that plane, they have simulation time, simulation hours. So I thought about this concept of saying farmers probably will enjoy having simulation hours. So we build a simulation that basically what it does, if you grab any yield monitor data sets, I mean, you put it there, the yield monitor, it kind of simulates, if you start selecting different plant densities inputs, it simulates what happened in your field with the different inputs, because we have responses to plant density, so you can start playing to see what happens, and you can have an economic analysis, so you can play with that to say, okay, what happens if I increase the seed rate here? So it's kind of a start basically talking to our stakeholders and agronomists in a different way. We are saying, okay, we have the research, but now we are converting the research into a decision, but it's data-driven decision, okay? I mean, this one is super simple. We grab data from multiple sources, and some people say, well, I'm doing this salt test and I need to correlate yield versus, and if you look at the different methods, and Jeff knows this, there are many methods. And we say, okay, what about if we build an app that we just put all the methods there, and then the people, what they should do is only just to put relative yield and the nutrient status. Something simple, you just upload that, and you're gonna start playing. Oh, I would like to test a different method. Oh, I would like to turn my target to 90%. So think about all the applications that you have in your side that you can build these type of applications, no? Metrics. Many times I was working, for example, this is something that I have a student that he enjoys so much metrics. And I say, okay, you enjoy much? So he built this package that basically what it does is anytime that you are building like a predictive versus observe, how many times you are looking at something that you say, okay, I want to build a predictive versus observe model. So here, this package helps you to do that. And it helps you to basically saying, well, there are so many metrics, R square, mean absolute percentage error, root square error, partial balance error. These are all the type of determinations, and there is a glossary on the application that you can check to say, what are the best type of metrics when I'm looking at predictive versus observed to know that my regression is good. And this is, for example, for remote sensing. So you could just grab any of your data that you are using, for example, predictive versus observed. You want to compare something that you collected from the field versus a sensor, and you want to know how close they are aligned. So you can use this package. We have many examples there, and you can easily just apply it, okay? Super simple. And then this is something that we did before we left K-State as a kind of a farewell gift. We put all their 40 years, I mean, it's close to 40 years data in terms of variety trials. They have 40 of plus years of data for corn, soybean, sorghum. And I say, do you guys have any copyright trademark on this data? No, okay, good. What is that? So, and what we did is like, okay, I mean, farmers, no one has access to this data. This data was on PDF, it was on the web, and the new data is on Excel files. So if a farmer wants to compare one hybrid versus another hybrid in a different year, how do you do that? And then sometimes what happened was that they were harvesting one field in October and they were sharing this book to the farmers in February. I'm talking to the guys and saying, the farmer decide the seed, if he harvests October 1st, October 2nd. The farmer will not wait, not today, on basically purchasing new hybrids. In fact, the companies are so aggressive now that they're gonna go to the farmer the day that he's harvesting. And then they're saying, if you buy today, I'm gonna get you this and t-shirt and a hat and, and I will throw also something else. So, I mean, the challenge of making sure that you are relevant is sometimes about timing. You cannot just harvest in October, variety trials or whatever it is, and you will say, I'm gonna share with the farmers in February. And most of the times when you share with them, it's static. You show on a slide and you say, you see? And you say, but wait, farmers can enter to this website. They can just click there. They can look at the last 40 years of data by crop. They can just compare different locations. They can compare hybrids. And you can do it the data they're harvesting. I say to the lady, send me every year the Excel files, and we can upload it. The data you're harvesting, send me the Excel file, and it's gonna be there already. So here are examples you can select because we have canola trials. So we can select, for example, Indiana. So we can look at data from Indiana from canola, number of years. We can start comparing different, I can express in bushels per acre, tons per hectare, whatever I want. I can filter varieties, I can add. So these tools are not too complex. I mean, and the students that are there, if they wanna do something else with your data, this will be good ways to visualize your data. So, and the beauty is that someone that is using these, then they can get all the data. No? They can basically extract the data and take it with them, which is good. So let me close because I wanna make sure that I don't spend too much time. I wanna close with something that is a little more positive and forward-looking and also just talking specifically to the students. So we have two surveys. We have one long-standing survey at Purdue, that is the Crop Life Precision Ag Survey, that basically is asking to every year to all the retailers, what are the major things, skills, or that the retailers are seeing or the changes in technology adoption. Then this year we came up with this survey that we put together that was directly asking farmers, not retailers, directly asking the farmers to say, what do you think about AI? So to keep it simple, what we found is that the farmers are saying that 55% of the farmers agree that artificial intelligence will help them in the decision-making in the future years, okay? And if you look at the Crop Life survey, this survey has been running for the last 20 years. And if you look at what happens on this question specifically, AI will lead to better agronomic recommendations. You see that 45% of the retailers are now just saying that AI is going to lead to better agronomic recommendations. So what I'm just saying with that is that we have retailers, farmers, and then if you look at from the workforce perspective, there are two reports. There is one report that is the Markets and Markets report that is talking about how agricultural analytics is going to increase close to $3 billion in 30 years. And the McKinsey reports that is estimating that digital ag is going to be adding to close to 500 billion in a global GDP. And this is a report that I think that is not published yet, but I hope that it's going to be published soon. That is from Purdue. That is going to show that 40% of the undergrad students on the job market is requiring now more data science skills. Okay. So what I'm saying with that is that the demand for data science in agriculture and artificial intelligence is going to be increasing exponentially. Okay. And the question is, what are the things that we're going to do to train people to be ready for that job market? Okay. And with that, I'm not saying that I don't want to have experts on many special topics. In fact, in my team, we have experts on many special topics, but they need to know how to do some other things. They need to know how to code. They need to know how to talk. They need to know how to be a little bit more interdisciplinary, to be a little bit out of the comfort zone. And you see that one of the things that I'm excited to see on that report is that this shift already happened in many disciplines. There are many disciplines like ecology and some disciplines connected to agriculture that they already are more quantitative, that they already are asking people for more data science skills. So it's nothing that is new. I mean, it's nothing that is surprising for me. And the other thing is that most of the job market is going to pay more for people that they have those skills. I will leave it here, and I will say that I did that with AI. So this is my disclosure. It took me around 5 minutes. I prompt the AI image generator, and I say, I need a Purdue tower clock that looks futuristic. And the first one was okay, but I say, give me more futuristic. And then until the third one, it gives me this one. So and I said, yeah, that's good enough. Okay, but these are the things that you can start incorporating AI in many of the things that you do every day. Like there is a really good website. I mean, as a Digital Ag Institute, we have seminars, lunch seminars. The Purdue Libraries has a really good website on all the AI tools, from research, from meta-analysis, from synthesis analysis. So if you really are trying to test new things, you will be quite surprised how much AI can help you. And I will say, I use AI quite a bit. I use AI for this. I use AI to brainstorm with me. I say, okay, I need a catchy name for a title. And I just play with AI a little bit, 5 minutes, done. I usually say to everyone, don't have to be afraid of the AI. AI is going to be our personal assistant. And hopefully what it's going to do is going to be helping us to be more efficient. That's the main goal of the AI. But I think that as long as you slow down and you don't really incorporate AI in your daily routines, it's going to be taking longer than that to start adding those into your daily routine. So my goal, as Christian was saying at the beginning of the presentation, the question is, what we want to do with the Digital Ag Institute is start bringing people together. So that's our main challenge for the future. Because as I mentioned at the beginning of the presentation, many of these challenges is not an agronomist only. We need an agronomist working with a plant pathologist, with someone in horticulture, someone in computer science, someone in civil engineer, someone in data science, and think about how we're going to do that, how we're going to do building those teams. I think that's one of the biggest challenges that we're going to have for the future. It's not connected to the technology per se. It's connected to how we will be able to build multidisciplinary teams effectively. That's all. Thank you.
Question for Dr. Ciampitti?
Any students?
Yeah.
Yeah, so farmers are collecting massive amounts of data, right? And the issue that I think may surface is actually one, proprietary rights, and then second, access. And so, there's a lot of potential that we could get in terms of, using models and predicting yields and stuff like that, if we had access to, the data that the farmers have, but are keeping it close to their chest. So what recommendations do you have in terms of improving access? And then what's the What do you think about preparatory rights of that data?
I would say that long term, that's an excellent question. What I have seen long term is that, I mean, at least with the farmers that we are working, is that they kind of, that trust is building up. And then I think that they are already seeing that they are already sharing too much data with other dealers or with other companies. So that I think that we are gonna lose that problem of farmers not sharing the data. I think that farmers are gonna be more open on sharing data. One of the things that I mentioned at the beginning is they're only gonna incorporate a technology, and we have that on the survey that we did, if brings some economic value. Simple as that. So if you bring me a tool that it looks nice, that I can show you a map, they will look at that, they will use it for 1 year probably, and they will pay you for 1 year, and the second year they will say, thank you. So unless the tool give them more money or save them time, because that's the other thing that they mentioned, time is critical for them. If they could be, many times they are away from the family, working on the fields, planting, harvesting. So if they can have something that is solving those problems, they're gonna pay. So that's why we look at now autonomous. And then we see a very promising opportunity because, but again, it's very challenging because how do you start connecting a machine that drives itself, but then we need to start looking at sensors and connecting the data from the field and make sure that it's data science or data driven, and it's agronomically sound. But those are the things that they're gonna start providing solutions that are gonna be real solutions. So I'm gonna see that the next 10, 20 years, they're gonna be very transformative on that end. And you see that from many of the technologies that we can enumerate, thousands of technologies on the last 10 years, you see that farmers only maybe adopted 5. Like GPS, yield monitor. So the ones that they really make sense and they are simple are the ones that they are adopting. The other ones that they look at the beginning super fancy and nice and say, no, you can enter to this website, you can have natural recommendations and you can do this, you need to pay $10 per acre. They will do it for 1 year, for 2 years, and then the 3rd year, they already know how to do it. And when the margins, if you look at the margins today, they are so thin that it's impossible for them to put them more pressure. So that's why we talk to companies many times. And if companies want to monetize digitalization as an added, it's going to be very challenging for them. But if they want to put that digitalization as okay, I'm selling you seeds, fertilizer, and here is a tool that you can use for digital records, for keeping, that will be the way that I think that the companies need to figure out what is a business value. Mm-hmm. Because many of the companies that they try to charge extra, they basically fail.
Well, what if the information was for sale to a commodities trader, for instance? Who is ultimately I'm just thinking of all the other information that we give out for free. I'm wondering who ultimately will be the purchaser of this information. Will it always be the farmer?
No, in fact, I'm fortunate to say many times today, the people that are the ones taking the decisions are retailers. The retailers, because of the system, many situations, the retailers are the ones providing recommendations and saying, you should do this. Mm-hmm. And I have farmer friends, that they just almost follow exactly what the retailer is telling them. Directly, because it's a friend, because they know each other, but they go and saying, retailer recommended to do this. So when you look at your potential, if you want to say customers, most of the times, retailers are really a big piece of the operation, because most of the times, even the introduction of technologies, they go through them. Because if they have a new technology that is promising, they will be the ones offering that as a service to the farmer. And most of the times, I think that technology adoption will happen like this. For many farmers to buy an equipment or a very expensive piece of equipment is going to be very challenging now. Mm-hmm. But to access and to basically use a service from the retailer is going to be much better, because you are not basically having a sunk cost, paying something that is too expensive, and then you are only accessing to a high level of technology, but you don't just take care of the maintaining. Mm-hmm. mean, depreciation, everything. You just access, use it, someone is coming, using it for you, done. So at the end of the day, you are only just taking the decision, do it or not.
On the topic of uncertainty, how do you see that changing in the next 30 years? Right now, we're the ones, people going and discussing with them about what's going on, but there'll be a point where they are gonna be taking care of that based on the information that is available to them.
When we talk to many people about uncertainties, because sometimes we have conversations with retailers or companies, and there are companies or people that they say, we want to be super precise. We want to know exactly what is your optimal input in each field. And then what we say to them is, be careful, because many of these decisions, they have a high degree of uncertainty. So, and I'd rather have a model that is not that precise, but basically is more profitable for the farmer. Because you're trying to sell something to the farmer that is, it's super size specific. But then when you look at uncertainty, you say, for example, the optimal end rate for many of these fields, they have a plus minus 30 pounds. So then basically the farmer could apply 180 or 200, and basically the yields were going to be very similar. So there is always some degree of uncertainty, because many of the decisions of inputs are connected in many situations with the weather. What the weather is going to look at flowering. That's why also I believe that the transformation of the autonomous is going to be helping us to move a step forward, because so far, if you look at the adoption of in-season applications, except for herbicide or fungicide, other inputs like nitrogen hasn't been adopted. Why? Because I don't see a lot of profit. I only save 20 pounds, 30 pounds. That's not enough to make up. But if you see about being more precise, okay, well, if I can get access to autonomous and I can have a machine just doing the applications. So then I can save money on time of myself. I have less workers, and I can also make sure that I have a more precise application of nitrogen in the fields. But the uncertainty is something that, unfortunately, we need to start talking, because at least in agronomy, I'm not sure how it's in botany and plant path, we haven't done a good job on talking about uncertainty in agronomy. Most of the time we always try to be so specific and fitting a model and saying, I have the optimal for this. We focus so much on that we didn't focus on really start calculating what is the probability that this could happen under this environment with this weather, and what is the real uncertainty of taking this decision. And letting the person that is taking the decision to decide based on the risk level. Not telling the person 150. Because what we are doing is we're taking all our science, and then we're dumbing down in a way that basically people will say, well, yes, that's agronomy. But it's a lot of science behind that. And it's not just agronomy. The problem is that if we try to simplify too much, as they're asking most of the times and saying 150, we are basically undermining the things that we do. We're just also reflecting that what we do is super simple to do. And we know that it's completely the opposite.
Past the hour. Is there any last question? Not? Let's give him.
You're gonna feel really bad.
Flavor tea. Yeah, so they make like they have a tea line. They got blueberry. Variety. This is just their sweet tea version. Have less carbs. This is I guess some. It's like sweet tea, but it doesn't have all the carbs with it. So.
Is it okay? No, I found. Yeah, I can't remember his name.
So you start seeing some.
Okay.
Now that we are talking about